Okay. So these are the instructions for how to write hybridization and bonding schemes. Hey guys, could you stop talking, please? Thanks. The first step is to write the Lewis structure for the molecule, and then we're going to use VSEPR theory to predict the electron geometry. We're looking at the number of electron groups around the central atom. Based on the number of electron groups, we're going to select the correct hybridization, and that's just based on the number. Then we sketch the molecule, and we're going to show overlapping orbitals, and then we're going to label all the bonds using pi or sigma notation. The good news is you will not have to do this on an exam, but there's a worksheet 11, and you will need to be able to select correct hybridization and label bonds, but I won't make you draw these crazy things that I'm going to draw today. So the first example, write a hybridization and bonding scheme for xenon tetrafluoride. So we have to start with the Lewis structure. And I'm going to do these fairly quickly because that's not the point of this part of the lecture. So we've got 4 fluorines around a xenon, and then we have to figure out how many electrons there are, valence electrons. So I have 4 fluorines, 7 each, and xenon has 8 electrons. So that's 28 plus 8 is 36. And then each of these bonds is 2 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 2 more pairs of electrons. Xenon is large enough to expand its octet, and so we'll put those extra lone pairs on the central atom. Okay? That's step 1. Now, we're going to look at the central atom and identify how many electron groups are there. Remember that a lone pair is one group, a single bond is one group, a double bond is one group, a triple bond is one group. Because it's a group, it's not a pair. So how many groups of electrons do we have? 6. We have 6 groups. Whoops, wrong pen. 6 groups. And so if we think about xenon's valence shell of electrons, we've got S and P and D because xenon is in period 5. So this is 5S, 5P, and 5D. I need 6 orbitals. I need 6 hybrid orbitals, so I need 6 regular atomic orbitals to hybridize. So I'm going to take this one, 1, 2, 3, 4, 5, 6. So the hybridization then is S, P3, D2, because I'm going to use the S orbital, all 3 P orbitals, and 2 of the D orbitals. Any questions about that? Now, the fun part is the drawing. Just to help us see what's going on a little bit better, I'm going to draw the orbital diagrams for xenon and for fluorine. So for the xenon, we've got these 6, right? And then there's each of the fluorine atoms is going to overlap a half-filled orbital with one of these half-filled hybrid orbitals on xenon. And so we can attempt to draw that. So here's xenon. Xenon has these 6 hybrid orbitals, and what shape do 6 balloons take? It's over there in the octahedral? Yeah. That's what you meant. So octahedral, we've got one going up, and one going down, one kind of going back, and one sticking out in the front, and one going back, and one sticking out in the front. Looks like a weird flower. Pretend it's three-dimensional. So each of these, well, not each of them, two of them have lone pairs. So then we have to decide where those lone pairs going to be. So here's our octahedron balloon structure. In the octahedral structure, all the angles are the same. So we'll make this pink balloon here the first lone pair. Where does the other lone pair go? On the opposite side, because they want as much space as possible. Stay. So we're going to have a lone pair here and a lone pair here, and then these guys are going to be half filled. So then our fluorines, so here's a fluorine. We're just going to draw the half-filled orbitals on fluorine to make it a little easier to look at. So fluorine has a p orbital that's half-filled, and that overlaps with a xenon half-filled orbital. And so each of these fluorines takes its one half-filled orbital and overlaps with xenon's half-filled hybrid orbital. Any questions? Can you see why I'm not going to make you draw that on an exam? Imagine trying to grade those. Not pretty. I do this for a living and I can't do better than that. So the hybridization is the sp3d2. And the bonding, we want to be able to label these bonds using the notation that we learned. So here's a bond, and this is between what kind of orbital on the fluorine? The p orbital, right? And on xenon, what kind of orbital is xenon using? It's using this hybrid orbital, right? How are those orbitals overlapping? Are they overlapping end to end or side to side? End to end. So that's a sigma bond. Oops. So it's a sigma bond between xenon and fluorine. And then in the parentheses, we tell what kind of orbital that element is using. So all four of these bonds have the same description. They're all sigma bonds between an sp3d2 orbital on xenon and a p orbital on fluorine. Any questions? Let's do something similar for HCN. Again, we need the Lewis structure. No, it's not very pretty, but it'll do. So there's our Lewis structure. So carbon is our central atom. How many electron groups? Just two. The triple bond is one group, and the single bond is one group. So we have two electron groups on the central atom. That tells us what hybridization to use. So here we've got carbon, and if we look at carbon's valence shell, this is the 2s and 2p, right? Two electron groups means I need to take two of these orbitals and hybridize them. I'm going to start with the s and then work my way over to get however many I need. So this is going to have sp hybridization. So I'll have sp, and then I've got two p orbitals that are just left sitting there. So this is carbon. Carbon has 4 valence electrons. We'll put them in here. When we hybridize S and P, the energy level of this goes higher than the S, but it's lower than the P. So it gets much closer to the energy of this room, or of these orbitals. So this next electron is only going to have to spend a little bit of extra energy or a little bit of extra money to get his own orbital, his own bed. So like, if you're paying $50 a night for the hotel room and it's going to cost you 50 cents to get your own bed in the next room, I think everybody would agree that would be worth it. But if it's going to be $25, no, that's just too much. So the 4 electrons from carbon, what we'll find is they will always separate like that because carbon makes 4 bonds. So here we have 4 half-filled orbitals. And when we look at the Lewis structure, we see that carbon does have 4 bonds. There are 2 electron groups, but there's a single bond here, and there are 3 bonds in the triple bond. And so then we can look at hydrogen. Well, hydrogen is nice and simple. Hydrogen has just 1 electron in the 1s orbital. And then nitrogen, we're going to assume that this is not hybridizing. So here we've got 2s and 2p. Hydrogen has 5 valence electrons. So we're going to stick them in here. 1, 2, 3, 4, 5. Nitrogen has 1 filled orbital. That corresponds to the 1 lone pair that we see here. Okay. So here's carbon, here's nitrogen, and here's hydrogen. So carbon is using sp hybridization, so I'm going to draw those hybrid orbitals first. So there'll be 1 in this direction and 1 in that direction, because that's what 2 balloons do. They make a linear shape. Each of these is half filled. What else does carbon have going on? So I just drew these guys. It also has 2 p orbitals. So I'm going to draw those as well. One's going straight up and down. That has an electron in it. And one's coming out at us. Again, those are harder to draw. Let's do hydrogen next because it's a little simpler. Hydrogen has just this 1s orbital that's not hybridized. And so we represent that in blue. That didn't go very well. Let's do this. So hydrogen's half-filled s orbital is going to overlap with 1 of carbon's hybrid orbitals. And then over here we have nitrogen. Nitrogen has this lone pair, the 2s. I'm not going to draw that because it makes it a bit complicated. It's already kind of a mess. So hydrogen's going to take 1 of its p orbitals that's half filled and overlap with the hybrid orbital of carbon. It has another another p orbital that goes straight up and down, and another one that goes in and out of the plane of the screen. So this p orbital and that p orbital can form a pi bond. They will do this side-to-side overlap thing. And so that'll make a bond. And then this other one, I'm going to make it a little darker so we can maybe tell them apart. Maybe. These are coming in and out of the plane, but these are also going to form a pi bond. Any questions? That was pretty silly, huh? Like I said, I'm not going to make you draw these things. On the worksheet, what we can do is we'll start with the original unhybridized orbitals for the central atom. We'll look at the number of electron groups, and from that we'll choose the hybridization and put the valence electrons in there. We will look at the unhybridized orbital diagrams for any other atoms, and then we're going to look at, well, how are these going to overlap? Well, the sp is going to overlap with an s here, and the other one is going to come down here. Maybe I can show that. Oops, it's not what I meant to do. So, these guys are overlapping, and these guys are overlapping. And then this guy is overlapping with that guy, and this guy's overlapping with this guy. We're not going to draw those lines. Now we're going to label these bonds. So this carbon-nitrogen bond here, this one in the middle, is that a sigma bond or a pi bond? It's a sigma because it's an end-to-end. Hybrid orbitals always make sigma bonds. So that's a sigma bond. This guy right there. That's a sigma bond between which two elements? Carbon and nitrogen, right? Carbon, I'm going to leave space for the orbital. Nitrogen, I'm going to leave space for the orbital. Well, what orbital is this that carbon's using? It's a hybrid orbital. It's an sp hybrid orbital. And what's this orbital that nitrogen's using? It's just a p orbital. So that's the label for that bond. And let's look at this one. Sigma or pi? Sigma. Again, this is a hybrid orbital. Hybrid orbitals always make sigma bonds. You're like, well, it's not overlapping the end of the s orbital. Well, the s is a sphere. It doesn't have an end, but it's overlapping the end of the hybrid orbital. So this is a sigma bond between carbon and hydrogen. And what kind of a orbital is carbon using? It's using an sp, right? And what kind of an orbital is hydrogen using? S. And then we have these two other bonds. These have the same notation because they're the same elements and the same kinds of orbitals. These are the pi bonds. Right, so, right, kind of looks like a pi symbol. And these are between carbon and nitrogen. What kind of an orbital is carbon using? A p orbital. And what kind of an orbital is nitrogen using? The p orbital. I'm trying to follow the color scheme of the book, where s orbitals are blue and p orbitals are red, and when you hybridize, you get purple. Pi bonds are always between p orbitals. You're never going to have a pi bond with a hybrid orbital. Any questions? CO2. Okay. I'm going to get the Lewis structure out here. How many electron groups? 2. 2 electron groups tells me I need to hybridize how many orbitals? 2. Right? So, here's carbon with its S and P, and I need to use 2 of those, right? So I'm going to take this one and this one. And so the hybrid orbitals will be sp, and then I've got 2 p orbitals that are left. Carbon has 4 valence electrons. 1, 2, that's bad. 2, 3, 4. And then oxygen, draw oxygen down here. We're going to assume that oxygen is not hybridizing its orbitals. It's got S and P. Oxygen has how many valence electrons? 6. 1, 2, 3, 4, 5, 6. Remember, valence electrons is the group number. 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Group 8, 8 valence electrons. That kind of stuff is on today's exam. Okay, so here with oxygen, we see that there are 2 filled orbitals there. Not very pretty. That's better. And that corresponds to the 2 lone pairs. So I'm going to draw the orbitals now. We've got carbon and we've got oxygen and we've got oxygen. And carbon has 2 sp orbitals that are half filled. And then it has 2 p orbitals that are half filled. There's 1. Make this one a little bit darker. And there's the other one. So that's representing these 4 boxes over here. And again, I'm not going to mess around with the lone pairs on the oxygens, but each of these oxygens has 2 p orbitals. So it's going to have 1 p orbital that it can overlap with the hybrid orbital of carbon. And then I'll have this one going up and down, half filled. And we're going to look at this one sticking in and out. And these can make pi bonds. It's a mess. This is just a mess. How are we going to label this bond in here? What kind? Is that sigma or pi? It's sigma because it's end to end. So we've got sigma, and it's between which 2 elements? Carbon and oxygen, right? What kind of an orbital is the carbon using? It's using one of these sp orbitals, the hybrid orbitals. And what kind is oxygen using? We're looking for the half filled, yeah, p. So that bond and this bond have the same description. They're both sigma bonds between carbon and oxygen. And then we have these other bonds. There's one over here and one over there, and those are the pi bonds, right? Pi. So pi bonds between which elements? Carbon and oxygen. It's the only thing we have going on here. And what kind of orbitals are carbon and oxygen using? P orbitals. Because the pi bonds are always p orbitals. The kinds of questions that you might have to answer on an exam for valence bond theory might give you a Lewis structure and ask how many pi bonds and how many sigma bonds are in that molecule. This is a double bond. The first bond is always a sigma. The second and or third are always pi bonds. So the first bond in each, there's 2 sigma bonds and 2 pi bonds. Could also ask, what's the hybridization on the carbon atom? And that's, look at the number of electron groups. That's how many orbitals you need. SP, 2 of them.